Welcome back. Last time we talked about virtual and physical memory. This time we're going to talk about how the OS provides an interface to manage dynamic memory and how low-level libraries can implement a dynamic memory management system for other applications to use. You talked about some of this in some detail in Precept last week, so I'm going to recap the big picture on those and then hit some additional items beyond the scope of Precept's very ASICS-tailored content. We often have data that our program cannot know the size of at compile time. For example, data that's dependent on user input. To handle this, one solution would be to guess. Unfortunately, if we guess high, that would waste memory, and if we guess low, the program would fail to handle at least some input cases. The more realistic answer here is to allocate memory dynamically. The partner of allocating memory is freeing it. And why should we bother? In principle, if we don't, the program could run out of memory. An especially pernicious version of this is a small memory leak in a very long-running program that just slowly eats more and more and more of the system's resources. Even if it doesn't run out of memory, the system has to keep track of all of our memory that we're using. We saw last time that the virtual memory abstraction is stateful. All our virtual pages are mapped into a page table, and when portions of our virtual memory isn't resident in physical memory, it has to be stored on disk. A subordinate issue is when the freeing should be performed. Some high-level languages, such as Java, automatically release memory that is no longer accessible by the program. This is great, the programmer doesn't have to do it, but it's potentially harder to reason about. Who knows whether at some specific time in the program, something remains in memory or not? Further, the manner of this automated garbage collection can be problematic. It can use resources, and in particular, it can use resources burstily. This may be fine for many programs, but I don't think you'd be happy if your car's braking system decided to freeze for just a little bit when it needed to do garbage collection. The other alternative is the programmer explicitly frees unneeded memory. This is what we see in C, explicitly deallocating the memory with the free call. The good thing here is that it's explicit, so there are no unexpected, badly timed pauses for garbage collection. The bad thing is, of course, that we have to remember to do it and have to get it right. So far be it from this class to claim that all programming should be done in C. Certainly for some applications, it just makes sense to use a high-level language, one with all the modern amenities. But there are some low-level applications, such as real-time systems as noted, or the OS itself, in which it is still common to program in languages without automatic deallocation built in. So let's take a closer look under the hood at the suite of functions that have come to feel like old friends, even if they might have been brand new to us only 8 weeks ago. Of course, in the current conditions, 8 weeks does in fact feel like a lifetime. We'll focus on malloc on free, because calloc is really just malloc in a memset, and realloc will follow naturally from how we define malloc. As we begin to think about how to implement a dynamic memory management system, our goals should be clear. We want to have good time efficiency, allocating and freeing should be fast, and good space efficiency. We shouldn't waste much memory. As you'll quickly find out, it's pretty easy to do one or the other of these, but quite a bit harder to do both. So for the rest of this lecture, we're going to focus on how malloc and free are implemented. For most of this, we'll be talking about how they manipulate the memory in the heap section, but near the end of this lecture, I'll also note a more advanced way of managing dynamic memory that doesn't use the heap at all. Ever since we introduced dynamic memory, we've been talking about the heap as the location where we have dynamic memory located. The heap is defined by 2 pointers. The heap pointer, indicated here as heap start, and the program break, the very end of the section. Beyond the program break is unmapped memory until eventually you hit the location of the stack at SP. Recall that when we push onto the stack, it's a lower memory address, so the stack and the heap converge. Initially, at the start of the program, the heap is of size 0. The heap pointer is the program break. They're the same. But we can move the program break to increase the size of the heap. To do so, we need to know about some system calls. There are two specifically that we need to talk about. One is sbrk, which is the deprecated method for moving the program break directly. It used to be that sbrk would be used to add or subtract a number of bytes from the program break and return a pointer to the memory location. But this is deprecated, and sbrk is only ever used now with argument 0, which returns the location of the program break. That pointer then is incremented or decremented and passed into a second system call, break, which sets the program break to be the pointer passed in. Thus, we can compose together a call of break on some manipulation of sbrk 0 to change the size of our heap. Each of the versions you've seen in Precept and you'll consider in Assignment 6 are built on top of these primitives. Our first two versions only use these two primitives. We'll call them minimal and pad. You know them as Heap Manager 1 and Heap Manager 2. One option would be to use the program break directly and no other metadata. Let's see what it would look like for malloc and free. Every time a client calls malloc, malloc would call break to expand the heap to satisfy the request, returning the old value of the program break as the allocation to the caller. And when a client calls free in this minimal implementation, let's do nothing. Our malloc implementation doesn't consider reusing any memory that was previously allocated and freed, so why bother freeing? Here's the very short code for this minimal version. Recall that static attached to a local variable will make it so it has process duration, and thus will keep its value in between calls. So now to analyze this version. In terms of time complexity, malloc looks parsimonious, but is in fact tremendously expensive, because break is a system call, and thus every single call to malloc will have to invoke the operating system, which is very slow. And in terms of space, there's no reuse at all. Every single malloc makes the heap bigger and bigger and bigger. This is a strawman implementation, thought experiment if you will, just to set a baseline. It's in no way feasible. But let's address the time performance first, because we have a large address space to expand the heap into, so we can ignore that problem, at least for the moment. One way to improve time performance would be to amortize calls to break over many calls to malloc. We can do this by grabbing more from break than we need for any particular request. This implementation will have one extra pointer of metadata beyond just the location of the program break. That extra pointer will point to the beginning of the extra space we get back from break. Whereas before, every time a client called malloc would call break to expand the heap to satisfy the request exactly. In this version, when malloc calls break, it asks for a bunch more memory than the caller requested. It then returns the front of that new block to satisfy the request, and keeps the rest as a pad of additional space that it has gotten from the OS, but is not yet used to make an allocation. This means that the pad and the break pointers might not be at the same spot, but if the client requests more than is available in the pad, the picture is still pretty much the same. We call break to expand the heap more than enough to satisfy the request, return the allocation, keep the rest as the pad. And this becomes a win when the client requests an allocation that fits within the pad. In this case, we don't have to go to the OS, we can simply satisfy the request from the front of the pad, adjusting the pad pointer to accommodate the new request. Again, we do nothing with free at this point. We're always handling malloc with new, never-before-used memory from our virtual address space. Why bother giving up old memory if we're never going to use it again? We see in this version the code is a bit more complicated for malloc, but still not too bad. One special case for initialization, which will then also hit the case for having to make the system call. And whether we made the system call or not, the pointer manipulation satisfies the amount of the request from the pad. So now to analyze this version. We've fixed the time problem. With a large enough pad, we don't have to call break very often. So for programs that never call free until the very end of the process, this version is very reasonable. But of course, some programs do in fact call free. So now we can move on to looking at how we can implement free to have reasonable space efficiency. The key idea here is going to be reusing chunks that the user tells us, via free, that they're done with. And the barrier standing in our way for that is fragmentation. Once we have a free function that finally does something, we'll have a mixture of chunks that are in use and chunks that are free, the latter being available to allocate again. In order to maximize the ability to allocate these free chunks, the dynamic memory management system must minimize fragmentation, which is a condition in which there's sufficient total unused space to satisfy a request, but malloc cannot actually use it to do so, and so instead has to request more memory from the heap. The first kind of fragmentation we'll cover is external fragmentation. Consider a request for 150 bytes from this heap. There are 150 bytes available, but not in one contiguous chunk. The Dynamic Memory Manager can't move the in-use chunks around. That would cause dangling pointers in the client. So there's no way to get the 100 and the 50 together. Instead, we'll have to go to the OS to request it to expand the heap. For external fragmentation, I like to make the analogy of a notebook, where you want to tear out a page to write a note to a friend, but you've written on the front side of every single page in the notebook. So even if you've never written on the back side of any page, thus there's plenty of room to write the note, there's no page you can tear out to give to your friend. The second kind of fragmentation is one which we've never experienced before, even if we were doing freeze. Up until now, we've always been satisfying malloc requests exactly. But some algorithms we'll soon see sometimes over-allocate. This can make sense. Consider if the client requests 98 bytes, and we have only one chunk big enough, a chunk of size 100. We could decide that, because we can't fulfill the request exactly, we should go to the OS and request more. But this seems silly. We've already established that we don't want to go to the OS more than we have to, for speed reasons, and so just giving the client the 100-byte chunk seems reasonable. What's 2 bytes after all? But this brings about what we call internal fragmentation, when there's memory that the client doesn't even know about, and thus if it's not being naughty it can't possibly use, that's trapped in its in-use chunk. To continue the notebook analogy, this comes about when you always start every entry in your notebook right at the top of a page. But you don't always write exactly full pages, and so the last page of each entry will have some space at the bottom that you didn't use, so it was over-allocated, but that no new entry can use. This is internal fragmentation. To demonstrate how a dynamic memory management system should minimize its external fragmentation, consider this artificial sequence of statements in the client code, and then the corresponding contents of the heap section that's managed by the DMM system. Imagine, if you will, again artificially, that the heap is of size 15 bytes. Initially, we have a ton of free space, well, 15 bytes worth, in yellow. This is just like the pad from version 2. For the first malloc request, we can fulfill it easily by just taking the front of the free space. Similarly, for another malloc, we continue to just allocate from the free space contiguously. And again, allocate from the free space on the heap. When the client frees its P2, though, we're no longer contiguous. The dynamic memory management system unfortunately can't move the block that P3 points to upwards in the heap. That would invalidate the client's pointer P3. There's no way for the DMM system to move an existing allocation except if the client were to call realloc on it. So this would be external fragmentation. The fragmentation would be realized when we try to allocate 8 bytes. Recall, we said the heap was of size 15, so 3 plus 4 plus 8 should fit. And indeed, there are 8 bytes free on the heap, but in a chunk of 1 and a chunk of 7. That means there's no 8-byte chunk, and we have to extend the heap to fulfill the request for an allocation. To avoid this phenomenon, whenever possible, we want to coalesce free chunks together. The chunks P2 and P3 point to here are a great example. Rather than a chunk of size 1 and a chunk of size 4, we'd much prefer a chunk of size 5. And making this change is safe. Dereferencing a dangling pointer is a memory management error, so clients shouldn't be impacted by the fact that the system combines these two free chunks. They shouldn't be accessing something they've already freed anyway. This then allows a new allocation to come in and use that chunk. And since we had space for 5, but it only asked for 2, it would be nice to minimize internal fragmentation by splitting the 5 into 2 to return and 3 to still be free. The client keeps freeing its memory, and the dynamic memory management system should continue to adapt and minimize fragmentation. So when the client frees P4, now the size 3 chunk that was split off from the size 5 chunk, the chunk freed by P4, and the remainder of the heap that was as of yet unallocated can all be merged into one large chunk. Similarly, when the last remaining allocation gets freed, we can merge together the free chunk before it, the newly freed chunk, and the free chunk after it. So in summary, a dynamic memory management system should reuse freed chunks where it can to minimize overall space usage, and coalesce freed chunks when it can to minimize fragmentation. But what it can't do to minimize space usage or fragmentation is reorder requests nor move in-use memory chunks. Now we come to the Assignment 6 baseline, what you know as Heap Manager 3. In this version, there's some new metadata. There's a list of free chunks stored in a singly linked list that is ordered by memory address. Each chunk contains a header with the size and a pointer to the next item in the free list if applicable. The free list is accessed via pointer to the first free chunk. The algorithm for malloc is to start at the front of the free list and find the first chunk big enough. If the chunk is of a size that it wouldn't be very useful to split, just use it in its entirety. This will create some internal fragmentation, but possibly avoid some external fragmentation. Update the list to skip over this chunk and return its payload to the client. In the case, though, that we first find a chunk that is much more than the client requested, we can split it up, as seen briefly in the fragmentation example slides. This means changing the header to be a smaller size and creating a new header somewhere in the middle of its payload to indicate the new chunk. This doesn't result in internal fragmentation, unlike if we had just allocated the entire chunk, but it does have some overhead, because whereas before you only had one header, now you have two. If we return the tail of the big chunk, the head is still free, so we can keep it in the list unmodified after the split. In the third case, there's no chunk big enough. We search the entire list, come up empty, so we have to call break to go ask the OS to expand the heap. We put the new memory as a chunk at the end of the list. It has to be there, in fact, because it's stored in memory order, and we're always increasing the size of the heap here, so the memory address of the new memory will be bigger than any of our previous chunks. If the last chunk in the heap previously was free, we should combine it with the new chunk. This reduces external fragmentation. When we free, we insert the freed chunk into the free list. In order to maintain the invariant that the free list is in memory order, we have to search for the correct place to insert it. Once we've found the right place to insert the newly freed chunk into the free list, we might find there's a free chunk immediately before it in memory, immediately after it in memory, or both. We should, again, combine them as much as possible in order to minimize external fragmentation. Here's the second step of that case, where we're actually combining 3 blocks into one. Before we do a full workup of the performance, think about this algorithm for free specifically. Pause the video and make your choice, then resume for the discussion. Recall that when we started out with good malloc time and good free time, but bad space. This fixed the space. We have some overhead and some internal and external fragmentation, but we have a functioning free, so we're able to minimize the number of times we must expend the heap. But at what cost? Our malloc now requires a search through the free list for a big enough chunk. Perhaps sometimes we'll find one quickly, since we're using first fit, but in the worst case, we'll have to search the entire list, and then still have to call break. And free, which was previously trivially, free, it also must search through the free list, and it must search until it gets the right spot, since it must maintain the ordering invariant. So our answer from the previous slide was D. It's even worse than order 1 with a bad constant. We'll attempt to fix this by throwing some additional data structure metadata at the problem to reduce the need to search the free list. Let's start by fixing free, since that merited the bold very in very bad. So now on to the doubly linked list version that you know as Heap Manager 4, aka the first dragon you must slay in Assignment 6. The key takeaway from the singly linked list implementation was that it was awful to have to search the list to find the right spot to insert a newly freed chunk. So our primary optimization here is that we'll just keep the free list in no particular order. This will allow us to insert in constant time by just stashing it at the front. But without the invariant that 2 consecutive chunks in memory that are both free will also be consecutive in the free list, we'll need to augment our data structure to have enough information to coalesce them together. We can do this easily enough by storing whether or not the chunk is free as metadata within the chunk itself. We'll see it as a flag in the header. Now our augmented data structure has the header with the additional flag, and after the payload, a new footer that, like the header but in reverse, has a size and a link to the previous item in the free list. Note that the metadata for accessing the list hasn't changed. We still maintain a pointer to the first item in the free list, but that is not necessarily the free chunk with the smallest address, like it is shown in this picture. The malloc algorithm hasn't changed a whole lot. We now have to set the status bit to in use, and we now choose to use the head of a split chunk since there's no longer an obvious linked list benefit to keeping the head in the list and using the tail. The free function also hasn't changed too much, except that we have to set the status, and most importantly, we can always insert at the front of the list. In fact, each part of the free function now works in constant time. Let's take them one at a time. Setting the status bit is minimal overhead added versus not having it at all. Insertion at the front is constant time versus linear in the linked list version. Checking whether the next chunk in memory is free with the linked list, we had to do this via the free list, which was the only indication of whether or not something was free. Now, with the status bit, we can use the size to find the next chunk, and then just look at that status bit. So linear has again been reduced to constant time. Similarly, to figure out the previous chunk in memory and whether it's free, we back up from our header to the previous chunk's footer, we use the size in that footer to find its header, and then check the status bit there. A few pointer operations, again, all constant time. And finally, if we are able to coalesce, we have to remove the chunks from the free list. But this is just stitching together pointers. A chunk's prev's next pointer goes to its next pointer, its next's prev pointer goes to its prev pointer. And once combined, again we insert at the front of the list in constant time. So we have a bit more overhead space, and it might lead to a bit more internal fragmentation, because more overhead means that the cutoff for not enough to be useful increases. But we're still reusing and coalescing, so overall space is still good. Free, our target for optimization, is now order 1. So all that's left is malloc. Let's keep going. And where we go next is your second foe, Heap Manager 5. To solve this problem, we again augment our data structure. In this case, the solution is drawn from the same inspiration as the hash table in assignment 3. If your downfall is searching a long list, why not have many short lists instead of one long one? In this case, the reason we have to search the long free list is to find a chunk of the appropriate size. If we separate different sized chunks into different lists, we won't have to waste time wading through chunks that are too small. The algorithms don't really change much at all. Just instead of one head pointer to the start of the list, we have multiple head pointers, one for each list. For free, it's as simple as picking the right bin and using that head pointer. For malloc, there's a slight added complexity that you start at the right bin, but it might be empty, in which case you try each successively bigger bin until you find a chunk. But once you find a non-empty bin, you can use the very first chunk in it. In terms of space, we again have some additional overhead, the bins. But we get the benefit of finding a perfect fit if it exists, so there's less splitting and thus potentially less external fragmentation. In terms of time, malloc is improved. For small chunks, it will never consider chunks that are too small. Even for large chunks, it will weed out all the small chunks before requiring searching a list of multiple sizes like in previous versions. Exact performance will depend on workloads. So that's everything that we'll be doing in assignment 6. In the last part of this lecture, I'd like to talk just a little bit about a few more advanced topics. Freeing memory is all well and good, but it doesn't really go away, does it? The client doesn't have it anymore, but the dynamic memory management system still does. It stays in the DMM system's data structure, and it stays mapped in virtual memory. It'd be nice if the DMM system could give it up entirely. And this is possible, in fact, but it requires a rather dramatic change. Dynamic memory not on the heap. Instead of using the heap, the program could ask the OS to give it an entire separate page from its address space all at once. This is something that is not a part of Assignment 6, but tends to appear in real-life implementations of malloc and free when dealing with particularly large requests. Our tools for this are two system calls, mmap and munmap. Mmap is a system call that creates a new mapping in the virtual address space, either at a page boundary near the specified location or at an OS-chosen one. munmap gives up a previously mmapped section. Notably, because it deletes the mappings for the entire range, any further references to addresses within that range will segfault, since they're no longer part of the program at all and thus not in the page table. This is how a typical call might work. The call requests from the operating system, I want an area of memory with at least n bytes that I can read or write, and I don't care where in memory it is. When done, the munmap call is a request to the operating system to take it off your hands so you no longer have to worry about it. This is the differentiator from our previous approaches. In those, free could put it back onto the free list, and plausibly the dynamic memory management system could check if the tail of the heap was all free and call break again to give it up. But here, the express purpose of the allocation is that when you free, you'll absolutely be able to give it up completely and have it immediately no longer be part of your running process. The implementation for this version is very simple. There's a header with a size and then the payload. That's it, since there's no need to link with other chunks. The code is similarly simple, because it's basically just wrappers around the system calls with a small bit of pointer manipulation to manage the header. But is this implementation useful? As far as space, it's pretty much perfect as far as the dynamic memory management system is concerned. One size T of overhead, no possible internal fragmentation, and the dynamic memory management system isn't managing the chunks themselves. So from its perspective, there's no external fragmentation concern. Think back to our first two versions, where we just asked the OS for exactly what we wanted and didn't try to reuse freed chunks. We're back in this situation. Of course, in reality, in memory, for external fragmentation, we've really just passed the buck to the OS to handle it. For time, though, we're also back into a situation in which each call to malloc makes a system call. Worse still, unlike the first two implementations, now each call to free does as well. But if we're allocating very large chunks, this might actually be worth it, because we just go out and get the large amount from the OS directly, rather than having to look through a list of large chunks and then probably end up having to go to the OS anyway. And then for free, we are sure to be rid of it and reduce the size of our page table immediately upon calling free. On our system, GNU Linux uses a combination of these, something like the bins implementation with the heap for small chunks and the VM mapping for large chunks. In the last few minutes of lecture, I'd like to offer just a couple of fun extra tweaks to the data structures that we've seen for dynamic memory management that can further optimize or empower them. The first one I'd like to mention is something that many people notice when they first see the doubly linked list structure. They look and say, wait a second, we have a payload, we have a forward and a backward pointer, but when we actually care about the payload, that is to say, when it's in use, this chunk isn't in the free list, so we don't care about the forward and backward pointers. And when we do care about the forward and backward pointers, when the chunk is in the free list, we don't care about the payload, because it's not in use. So we could in fact use the exact same data location for both. The very beginning of the payload and the very end of the payload could be where we put our pointers when they are not in use. This would decrease overhead because our headers and footers would be smaller. Another observation is that in previous implementations, malloc splits whenever the chunk is too big, even if it leaves some piddly little chunk in the end. We could do selective splitting. That is, rather than just saying, can this form a valid chunk, we could say, can this form a useful chunk? Can this form a chunk that's as big as we typically have in our workload? Can this form a chunk that's a third the size, a quarter the size, something along those lines? This would reduce external fragmentation because we would have more larger chunks, at the immediate downside of having increased internal fragmentation because we can't split as often. Another observation is that previous implementations will coalesce whenever possible, absolutely greedily. This is a bad thing when we have workloads that are something like malloc n bytes, then free them, and then malloc n bytes again. In general, this is a bad thing when we always have all of our mallocs be of the same size. When we do this, we free things, we coalesce them together, and then we immediately split back to the same size they were before. An alternative is deferred coalescing. We wait and coalesce many chunks together at a later time. This has the advantage for workloads like this, but it does complicate the algorithms because now you need to have some additional state to say, well, how long do you wait before you coalesce? Or you need to do additional lookups to say, how many chunks in a row do there need to be before you coalesce? I hope this lecture reinforced the details from Precept and helped you put them in a broader context. The last few slides have just been a subset of the appendix on this slideshow, and so there's some more potentially interesting further optimizations that you can make that are riffing on these same data structures and algorithms. So go check those out if your imagination has been piqued. Next lecture, we'll step back away from memory and back into the process abstraction as we continue our lower level systems and service level tour and prepare for assignment 7.